Hi, my name is PeterRoegen. I would like to start by thanking you for starting this presentation, the organizers for giving me the opportunity to give it, and hopefully also Scandinavian Airline System and the pilots for getting an agreement so that I can fly to the conference. I'll know in a little while. The algorithm I present is an algorithm for checking an structural alignment given by another program and to see if there's actually a topological obstruction from morphing the one structure into the other one as suggested by the alignment program. You can try it for yourself using my server here. Take the version 0.5, it links to instruction videos on how to use it and more about the theory behind it. So another way to put it is that sometimes, even though all the residues are in close proximity in free space, the entire chain need not be to be close in configuration space. And the example here, there is an oversliding change to an undersliding between the two structures, so you actually need to rearrange a large part of the protein to get from the one configuration to the other configuration. I'll come back to that example. By now in the conference it's probably said better by others why structural comparison of proteins is important, so I'll just take my own perspective on that. Coming from geometry and topology, I would like to give you notions of distance that makes sense on larger deformations of the structure, allowing you to include more structural data into whatever investigation you have, and making sure that it is actually similar, it's close in the configuration space, the data you take in. Now, if you have a coordinate-based structural alignment program, could be any one of these, and you could continue the list. Such a program provides you with a structure-based sequence alignment and an optimal superposition of the aligned subsets. This is obtained by optimizing some function that differs between the different alignment programs, but it's always a function of the distances between the aligned pairs of amino acids in the optimal superposition. And this is the same as scoring the distances that the alpha carbons traverse while doing the linear interpolation between the two structures. Simply just starting a straight line, making a straight line between the alpha carbon atoms in the two structures and interpolate them in time 0 to 1, going from the one structure to the other. And you could say the implied assumption generally is there's room for this morph, but perhaps it's not always the case, and therefore I have two questions that protein alignment obstruction give answers to. The first one is, are there going to be steric problems during this interpolation? And the next is the morph actually changing the topology of the protein structure. Well, steric problems are quite easy. The outcome is basically like a contact map. You find the shortest distance in time during the morph between all residue pairs, and if this is shorter than an allowed distance you could find in the PDB, then you start to have steric clashing between the two structures, and you get what we call an overlap. But more severely, sometimes the backbone actually passes through itself doing this linear interpolation, and the program then tries to resolve, saying some of these self-intersections are not really making change to the topology and others are more severe, saying they make an essential change to the topology. Again, it takes the alignment from another program. It's just an add-on to the original alignment score. So what is a self-intersection doing this linear interpolation? Well, it's at some point t between 0 and 1, you get a double point on the backbone where it passes through itself. It's actually checked that it's so-called a transversal self-intersection, where the line segment actually passes through each other. Inside the configuration space, this means that there is a submanifold here of self-intersecting configurations, and during the morph we pass through that, and that submanifold might actually extend quite far in the configuration space, so we try to see is it possible sometimes to get around these self-intersecting configurations. And sometimes it's possible. One of the ways it's possible if you have a closed loop like this. If at the time of the self-intersection this area and a surface here is disjoint from the rest of the protein, then you can do this trick and get from the one side, from the left-handed loop to the right-handed loop without a self-intersection. However, if another part of the protein actually is sticking through that loop, is poking through here, then of course it's not possible to do it without causing new self-intersections. So this is the check, is this surface disjoint from the rest of the protein at that time during the morph. Another possibility is that two self-intersections may occur in a situation like this one. You have sort of a loop passing through a strand here, and again, if the green surface is disjoint from the rest of the protein, you can sort of slide under and get back on top of the vertical part of the line segment here. So this is called the Reidemeister move of type 2 in knot theory. We can only avoid each self-intersection once, so we need to solve the optimization problem of getting rid of as many of the self-intersections as possible, and can actually do that in one optimization formulation where we also find the shortest path doing that, and the path length is basically the area of the green surfaces here that tells you how much additional motion you need to apply to the protein structure to avoid the self-intersections. The remaining self-intersections are then called essential because we think they make an essential change to the topology, or at least they require rearrangements of larger parts of the protein than the user is allowing the program to. So inside the configuration space, what is done, we start with one configuration here, end with another configuration here. The original linear interpolation is just a straight line between those 2 points that passed through self-intersection configurations, and what the program does is that it seeks in the neighborhood of this linear interpolation and see if there's a self-avoiding path between the 2 configurations, and in this case it's not possible. You actually need a larger detour than was allowed, so probably this self-intersection is going to be called essential, and the other ones can be avoided by the program. Couldn't we just use traditional alignment scores to detect these topological changes? The answer to that is sort of both yes and no, and the reason is that if you have the protein is a relatively thin tube, so the motions needed to go from an overcrossing to an undercrossing are actually quite small compared to the deformations you otherwise see in protein structures. So you can give an estimate of how small changes you need to make to a protein measured in different alignment scores in order to make such a change in the threading. An example here I made on a CASP14 model. The original model was in a distance of 3.5 angstrom, or a little bit less from the target, so not so bad. Basically meaning it was had deviations of the size that you see here over the most of the structure. But here I changed the model to be equal to the native structure outside the topological areas region here, because where the native structure has sort of two loops that are passing by each other, in this model it's actually poking through this loop here, and there are 300 residues in between, so it's a very long distance in the configuration space to get between these two configurations. The distance between these two configurations is only 0.4 Ångström in RMSD and a global distance test of 0.997. So this means that within really short distances in the configuration, measured with traditional alignment scores, you can actually have completely different threadings and knottings of your structures. So they might be not be present in the PDB, but computationally there's a very short distance to really different configurations. Now, does this happen in the classification systems? To answer this, we have a look at a set of CAF domains. They are relatively short. They are clustered at 60% sequence identity, and the shorter domain, the entire shorter domain is aligned to the bigger domain that's only allowed to be 10% longer than the shorter one. So if they are actually classified as being equal, these domains should be fairly identical. Now subdivide into alignments inside homology classes, inside topology classes, but not sharing homology, and between topology classes. You see, if we use the alpha carbon atoms as the curve representing the structure, you generally get about 3 times as many self-intersections in the morph as if you use a smoothing algorithm first. But using the Reidemeister moves of length up to 5 amino acids, the number of self-intersections left over, the essential ones, are almost the same. So this is sort of showing you a robustness of the notion of essential self-intersections. Inside the homology classes, you would find in 10 to 15% of the cases that there's actually topological obstructions for morphing the one structure into the other. Inside topology classes, this number would be something like 35% to 40%, depending again on how large deformations rearrangements you are allowing in the structures. Between fold classes, we actually see sort of the continuous nature of the protein fold space, because of course most of the alignments are between topology classes, and actually a rather large portion of those, 20 to 40%, can be done without causing self-intersections. So in many cases it's actually fairly easy to morph one fold into the other fold. If we do the same thing with TM align, and TM align is chosen because when I first submitted this work for the first rejection in 2015, it was the most restrictive alignment program. It only aligns residue pairs that are within 5 Ångström distance in the optimal superposition. Therefore, it aligns much shorter parts of the structures than the global RMSD alignment, and fewer self-intersections are found, but there are still more than 40,000 self-intersections in the aligned parts of these alignments in 140,000 morphs. So it's relatively likely that in most alignment programs you would find self-intersecting sections taking place, morphing from the one aligned structure into the other one. So the main finding is that sometimes structures you think are very close are actually not close in the configuration space. Sometimes it's relatively easy to morph from one folk class to another folk class. And I think this calls for new alignment methods, which I'm actually developing. So allow me this one last slide. In this work, we look for how big parts of the protein can we actually align such that we can remove all the topological obstructions using the omega moves. So in this example, there are 4 self-intersections in the morph of the full structure, and if you start in the N-terminus, you can see that you can go to almost to residue 120, and within that region it's possible to resolve the topological problems, but you cannot extend that, then you get an essential self-intersection. And if you go to start after that self-intersection, it's possible to get an alignment of the rest of the structure here. For each point here, we then get an estimate of how long a self-avoiding morph is between the similar portion of the alignment. This concludes my talk, with thanks to some colleagues that helped me in the process, and I'd like to thank you for your attention. There might be time for one question, so let me both ask it and answer it. So how do we treat alignment gaps here? Well, first of all, you need to fill in the gaps, and the reason for this is that if you, in considering the full structure without including the gaps, there might be a randomized move of type 2 here involved. If you now say one of these self-intersections belongs to a gap in the alignment and therefore we are not considering it, then it gets impossible to get rid of this self-intersection because we can only remove it by pairing it to the other self-intersection. So we need to take the gaps into consideration if we want to talk about topology of the chains. And the way it's done is simply by a sort of linear interpolation. You put in pseudo atoms at a shorter distance on the shorter sides in the alignment gap. And finally, is it nothing I'm detecting? No, it's not, but it's similar. It's similar in the nature that if you in knot theory go from one knot type to another knot type, then you need to pass through a self-intersection. But we are talking about open curves, so it's not knots in the mathematical sense. But anyhow, we did the experiment taking a protein with a knot, cut it quite closely to the end of the knot, and then aligned it to representative structures of similar length. And in almost all cases, there's an essential intersection between the knotted and the unknotted structures. There are only a few cases where actually the original morph did this thing that the ends actually go through a very large motion and unknots the structure. So you really need to be lucky that the ends are going out through the loops in the knot and untie the knot. Then it's possible to get find a self-avoiding morph from a knotted to a non-knotted structure.